In this video, I'm going to walk you through covalent shapes and hybridization. So we're not switching gears here from covalent. All right, this still is going to be these sharing of electrons taking place between these atoms. So the first thing we're going to look at here is called Vesper Theory. It stands for valence shell electron pair repulsion. You never need to know what the letters stand for. You just need to know what it means. And basically what it says here is that the valence electrons will try to get as far apart as possible in these covalent molecules, and sometimes this changes the 3D shape of the molecule. Okay, so the valence electrons are trying to get as far apart as possible, and sometimes this leads to some 3D shapes taking place. All right, so a lot of molecules here are not two-dimensional, which basically means they're not flat. They're actually 3D. All right, so what happens here is that sometimes in these molecules, when you have unshared pairs of electrons, and we'll talk about what that means in a second, um, these unshared pairs of electrons are held closer by your center atom, and this causes the bonding pairs to kind of repel. All right, and they repel from each other, and this creates sometimes these different shapes. Sometimes they're 3D, sometimes they're bent a little bit. All right, so the valence electrons try to get as far apart as possible, and sometimes this leads to some interesting shapes here for these covalent compounds. So the difference here between bonding pairs of electrons and lone pairs. Bonding pairs are the electrons that are literally shared between the atoms. So these, when you're thinking of your dot structures, these would be the electrons that are in between the two atoms being shared. Those are bonding pairs. They form the bonds. All right. Lone pairs are electrons that are not involved with the bonds, but are there on a particular atom in order to make it happy, in order to reach that magic number of 8 valence electrons. So we call those lone pairs. They're not directly involved with the bond, but they're needed in order to reach that magic number. All right, and a lot of times here, lone pairs will repel stronger than the bonding pairs. Okay, so if you look at these two pictures here, if you notice, each of these pictures both have a center atom. Over here on the left, it's pink. Over here on the right, it's orange. And they each have 3 things attached to the center. But if you notice, the one on the left is nice and flat. Okay, but the one on the right kind of has this bent down shape to it. Kind of looks like a little alien spaceship. And this is all because one of them has lone pairs on the center atom and the other one doesn't. Okay, so having those lone pairs cause these atoms, okay, to kind of bend. The electrons in the bonds kind of try to bend to get away from the lone pair of electrons. So we'll look at this more. So because these covalent compounds can do these, kind of weird shapes and bending, there's some common shapes here that we can look at. So I'll walk you through all the different shapes. You can pause it and look at the information, but I'm going to show you here what's important for these shapes. So I might go through this first one a little bit slower, and then I'll kind of pick up the pace here. All right, so the first common shape we see in these covalent compounds is something called linear. Okay, linear means basically it's in a line. So we say here that it's of type AB2. You don't have to remember that. That's just saying, hey, look, when you see a formula here of a compound, if it has one of the first element, two of the second element, kind of like BeH2, it's probably going to have a linear shape. Okay. The bond angle between the different atoms here is going to be 180. All right, so half a circle if you look up here. But the key point here that's important is the number of things attached and lone. Okay, so if you look here, this is what you need to know for each of these different shapes. How many atoms attached to the center and how many lone pairs are there on the center. So I just want to really make sure we're pointing out here that this is talking about the center atom. Okay, so we're talking about attached and lone on the center atom itself here. All right, so what we're saying here is if you draw a dot structure for a particular covalent compound and you see that the center atom has 2 things attached to it and no lone pairs on the center, you would automatically know that it has a linear shape. Okay, so to figure out these shapes, you draw the dot structure first and then you analyze the dot structure so you can just name the shape. People always think like, oh, do I have to draw the shape? No, you don't have to draw the shape. You draw the dot structure, okay, which you should already know how to do. And then after you analyze the dot structure and count how many attached, how many lone pairs on the center, that tells you the name of the shape, and you just have to name the shape, okay? So if you were looking at this particular picture here, this particular example, all right, if you look at the center, remember, you determine the shape by the center. The BE is in your center. So you literally count how many things are attached to him. Well, there's one hydrogen, two hydrogens. So he has two things attached. How many lone pairs are on this center atom, on this beryllium? Well, there's none. They'd be drawn as separate lone dots on the beryllium. There's zero. So this is two attached, zero lone. It's the definition of linear. You would just call this shape linear, and you would know in your head, like, oh, that means it's going to be in a line. Okay, so draw the dot structure, analyze the dot structure, look at the center, and that tells you the name of the shape. Okay, if you were going to study these, it's probably best to do like a flashcard. All right, you put on one side linear, on the other side, two attached, zero lone pairs. All right, just remember that it's talking about the center. So the next shape here is called trigonal planar. All right, again, I wouldn't spend my time memorizing the type or the bond angle. The bond angles really are just for your reference. I don't hold you accountable, make you memorize any of these bond angles. All right, what's important here is this: how many attached, how many lone pairs. So if you were to draw the dot structure of a particular compound and you look at the center and you say, okay, how many things are attached to the center? So for example, BF3. If you look at the center atom is boron here. How many things attached? There's 1, 2, 3 fluorine. How many lone pairs on the center? Well, there's zero lone pairs. So by definition, this shape would be trigonal planar. Okay, if you're given this, draw the dot structure, then you analyze the dot structure to name the shape. The next shape is tetrahedral. Okay, this one has 4 attached to the center and no lone pairs on the center. Okay, so far all of our first 3 shapes here have had no lone pairs on the center. But if you notice, this is the first shape that is not flat. All right, linear and trigonal planar were both flat, but this one, okay, has a 3-dimensional component to it. All right, it gets the valence electrons as far apart as possible. All right, gets a 109.5 bond angle here, so it has a 3D shape. So anytime you draw a dot structure and you have 4 things attached to the center, 0 lone pairs on the center, then you have the tetrahedral shape. Remember, the type and the bond angle are not as important as knowing how many things attached, how many lone pairs on the center. Next one here is trigonal pyramidal. Very similar to trigonal planar, but notice it's different. All right, so this shape, okay, would have 3 things attached to the center, all right, but 1 lone pair on the center atom. Okay, so that's what makes this different from trigonal planar. This one is not going to be flat. This is kind of going to have that alien spaceship shape to it. All right, so up here, all right, they're trying to show you this here. They drew these lone pair of electrons very, very far away here. If you were actually drawing this in a dot structure, you would probably draw it something like this, okay? You'd have the 3 H's around the N sharing a pair, and then you'd have this extra lone pair there on the center. Okay, so if you notice this, if you were to be given NH3 and need to know the shape, you would draw the dot structure like I did here. You would look at the center and you'd say, okay, there's 1, 2, 3 things attached, but there's 1 lone pair on the center. That means the shape is trigonal pyramidal. Okay, so you would label this as trigonal pyramidal, and in your head, you should know, okay, that's not flat. Okay, it kind of has this 3D component to it. Bent is a very important shape because it's the shape that water has. Okay, so anytime you have 2 atoms attached to your center and 2 lone pairs on your center atom, that particular molecule has a bent shape. So it's not linear in a line. All right, the atoms actually bend down to get away from the lone pairs of electrons here. So if you notice, all right, if you're looking at water here, the center atom is your oxygen. There's 2 things attached, 2 hydrogens, and there's 2 lone pairs on that center atom. So that's what makes this shape bent. There are electrons here in these bonds, and they are kind of bending down to get away from the lone pairs that are on that center atom. So anytime you have 2 atoms attached to the center, 2 lone pairs on the center, that shape is bent. Trigonal pyramidal would be the shape here that occurs when you have 5 things attached to your center and no lone pairs on your center atom. Okay, so if you look here in this picture, the center atom here is your phosphorus, and there are 5 chlorines attached to him. But on the center atom, there are no lone pairs. Each chlorine has lone pairs. Okay, those electrons are not bonded to anything, but the center has no lone pairs. Okay, so remember, to determine the shape, it's all about the center. Draw the dot structure, look at the center. The center atom has 5 attached, 0 lone pairs, so its shape would be trigonal bipyramidal. The octahedral shape is when you have 6 atoms attached to the center and no lone pairs on the center. Okay, so SF6 is a good example of this. If you notice, the sulfur is the center. All right, he has 6 atoms, 6 fluorines attached to him, but there are no lone pairs on the center. So the shape of this molecule would be octahedral. You can see there's kind of atoms coming out the top and the bottom and then the sides. All right, so this center atom, this sulfur, has to be able to expand to take more than 8. That's the only way this shape could work. But he is one of the elements that's able to expand and take more than 8. So anytime you have 6 attached to the center, 0 lone pairs on the center, when you do the dot structure, that shape is called octahedral. So the next shape here is square pyramidal. This is when you have 5 things attached to your center and 1 lone pair on the center. All right, so you can see here what happens is in this picture, instead of having an atom coming out the bottom here, all right, that lone pair that would be on the center, if you look up here, that causes these atoms to kind of shift upward and form a nice flat bottom. Okay, so it forms like a square, so the bottom's kind of flat, so they call this square pyramidal. But that would be when you have 5 things attached to your center. So if you look here, 5 fluorines attached to the center and 1 lone pair on the center. That's going to be square pyramidal. Remember, it's all about the center. So the last shape we have here is square planar. All right, this would occur when you have 4 atoms attached to the center and 2 lone pairs on the center atom. So if you look here, there are 2 lone pairs on the xenon. Remember, noble gases don't typically form compounds, so this is kind of the first compound we're seeing with a noble gas. Not only does it form a compound, but he actually takes more than 8 electrons as well, so it's kind of pretty bizarre. But this is actually a nice flat shape. If you look over here, this would be a 2-dimensional shape. So it's kind of different from tetrahedral. If you remember back, tetrahedral was 4 attached, 0 lone pairs on the center, formed a nice 3-dimensional shape to get those valence electrons as far apart as possible. But in a square planar here, you can see those extra lone pairs of electrons on the center cause this to kind of flatten out. Remember, Vesper says the valence electrons are trying to get as far apart as possible. And by forming this flat shape with these lone pairs on the center, that's how the electrons get as far apart as possible. So square planar is when you have 4 atoms attached to your center, 2 lone pairs on the center atom. So this is just showing some of the shapes we did. Keep in mind there are other shapes that we did not cover. There's more shapes you might see if you take AP or a college level chemistry class. Something like T-shape we did not cover. So we did hit a bunch of them, but just realize there are actually more. So I also want to do hybridization here real quickly. This orbital hybridization theory, you're not required to know a ton here about the theory or the background. You're more or less required to know how to use this or give the hybridization of a particular dot structure. But the basic gist here is that the orbital hybridization theory takes information about bonding and shape and kind of puts it all together here. All right, so you need to realize that when covalent bonds actually form, these orbitals that we talked about with atoms, these s, p, d orbitals kind of come together and overlap to form bonds. So for example, when you look at the compound BeF2, all right, when beryllium comes in, beryllium is in the S, so beryllium's coming in with an S, but then each fluorine is coming in with a P. So when a bond is going to form between a beryllium and one of the fluorines, these orbitals actually overlap and they actually fuse together. Okay, they hybridize. They form a new orbital here that we call sp. It's no longer s and it's no longer p. They actually come together and fuse to form SP. It's kind of like the idea that, you take a lion and a tiger and they make a liger. It's the same kind of idea here, is that we get a new hybrid orbital. Okay, so if you look at this picture down here, when beryllium forms a bond with fluorine, it's now an sp orbital. So we would say that this is sp hybridized. So the good news is you don't need to know a ton about the theory here. I'm going to show you what you need to be able to do with this. So these are the different hybridizations that exist. And usually there's a specific hybridization for a specific shape. Okay, so there's SP, there's SP2, SP3, SP3D, and SP3D2. Okay, so there's an easy way to do this. Okay, there's kind of like a little trick. All right, in order to determine a hybridization, you need to first draw the dot structure. Okay, I could give you an example and say, what's the hybridization of this? The first thing you need to do is draw the dot structure. Okay, and then what you do is you look at the center atom. Okay, and you count how many things are attached to the center atom. If there's 2 things attached to the center atom, the hybridization is going to be SP. Okay, and there's an easy way to remember this here. All right, if you have 2 things attached, all right, essentially there's one S, one P, and an SP, which equals 2. Okay, if you were to draw a dot structure and there were 3 things attached to the center, okay, we would say that that has sp2 hybridization. Okay, if you look and you count, 1s plus 2 p's equals 3 total. Okay, and so on and so forth. So if something was tetrahedral, if you drew it, there'd be 4 things attached to the center. So its hybridization would be sp3. 1s plus 3 p's gives you your 4. All right. Then if you notice, if you remember back to atoms, okay, the maximum number of boxes you would draw for a P would be 3. All right. So you can't have any more P's here. There's no P4s. All right. So that's when, if you had 5 things attached, okay, you would have to throw in the D orbital now. So that'd be sp3d. 1s plus 3p is 4, plus 1d gives you your 5. And then if something has 6 things attached, it'd be sp3d2, which adds up to 6. Okay, so it all depends on which orbitals are being mixed. But again, if you can look at a shape, okay, look at a dot structure, count the number of things attached, and make it work to one of these hybridizations, you can do what you need to be able to do here for hybridizations. So if I asked you to do the hybridization here for a particular example, so if I ask you to do this for CH4, all right, you don't just guess. You have to draw a dot structure. Even if it doesn't tell you to draw a dot structure, you have to draw a dot structure. So you have to go through your steps. First thing I do is total up valence electrons. So carbon is the first element. There are 4 valence electrons for each carbon, times 1 carbon in my compound here. Plus, there's 1 valence electron for each hydrogen, times there are 4 hydrogens in my formula. So when I total this up, I have 8 total valence electrons available. Okay, so carbons or nitrogens go in the center. All right, so I have a carbon, so he's going to be the center. Whatever's left goes around him. So I have 4 hydrogens. I'm going to place them evenly around the center. Whoever's next to the center has to share at least a pair with the center. Okay, so I'm going to show my covalent bonding here, and then I have to make everybody happy. If you look at this picture, carbon has 8 around him, hydrogen, each hydrogen has 2. Okay, everybody's happy. When I total it up, it equals 8 electrons. So this is the dot structure for CH4. Okay, so now I literally count to determine the hybridization. Okay, so I say, how many things are attached? All right, so there are 4 things attached to the center. Obviously, there are 0 lone pairs on the center as well. All right, so you could use this to determine the actual molecular shape here. This would be tetrahedral. All right, 4 attached, 0 lone pairs on the center is the definition of tetrahedral shape. All right, but if you want to do the hybridization, there are 4 attached to the center. Okay, so if there are 4 attached, all right, your hybridization for this molecule will be sp3. 3 p's plus 1 s gives you your 4. All right, so that's how you determine hybridization. Draw the dot structure, look at the center, count how many things are the center, and make sure when you give the hybridization the superscripts essentially add up to the number attached. So now what if I wanted to do the hybridization here for SF6? Same deal. All right, when I want to do a hybridization or I want to do a shape, I have to draw the dot structure. So there are 6 valence electrons for each sulfur, times there's 1 sulfur here, plus there are 7 valence electrons for each fluorine, times 6 fluorine. All right, so when I total this up, I have 48 valence electrons here. So that means I need 48 dots in my picture when I do this dot structure. All right, so carbons or nitrogens in the center, there are none. So whatever atom there's less of goes in your center. So the sulfur is going to be my center. Whatever's left has to go around him. There are 6 fluorines left. So immediately I know that sulfur is going to need to be able to expand because that's the only way he could take 6 fluorines here. Okay, so you put your 6 fluorine around your sulfur. Whoever's next to the center has to share at least a pair with the center. And these bigger ones here gets a little bit tougher to kind of show this correctly without getting the dots all bunched up, but do the best there that you can. So whoever's next to your center shares at least a pair with the center, and now you make everybody happy. Well, right now, sulfur is good. He's actually over happy. He's got 12 electrons. He's expanding here. But each fluorine only has 2. So each fluorine needs 6 more, okay, valence electrons. So I'm going to make every fluorine happy. Remember, if you're wrong, you'll figure it out in a second. Again, it's very easy here to, mix up which electrons go with which. So be very careful. All right. So I gave each fluorine the number of electrons he needs. Each fluorine needs 8. When I total up my valence electrons, now everybody's happy and I hit 48. So this would be the dot structure here for SF6. So now if I want to do the shape or the hybridization, okay, I literally look at the center and I count. So the sulfur is the center. There are 6 attached to the center, and there are no lone pairs on the center. The fluorines have lone pairs, but the center, the sulfur, does not have any lone pairs. All right, so by definition for shape, okay, this would be octahedral here, okay, because there are 6 attached, 0 lone pairs. All right, so that would be the definition of octahedral. Now, if you want to do hybridization, all right, your superscripts here for your hybridization have to add up to 6. There are 6 attached. So the hybridization for this is going to be sp3d2. All right, 1s plus 3 p's plus 2 d's gives you 6. Just a little more info here with these hybridizations. Anytime you have single bonds in your molecules, you kind of do what we just did, where you count, all right, the number of things attached to the center and make it work with the numbers. Anytime you have double bonds in your molecule, all right, just by default go with sp2 as the hybridization. And anytime you have triple bonds in your molecule, just by default do SP. It would still work with the counting, but it's just a little bit easier to just remember, hey, look, double bonds, sp2 hybridization, triple bonds have sp hybridization. Real quick, I just want to mention sigma and pi bonds here. So sigma bonds are when the electrons are located around the center axis of the bond. So if you look here in this picture, if these are your two elements here that are sharing electrons, if it was a sigma bond, the electrons would be right there in between the two atoms. Okay, so a sigma bond is when the electrons are literally being shared right between the two atoms. So all single bonds are sigma bonds. Pi bonds, on the other hand, are when the electrons are actually located above and below the axis here of the bond. So you don't need to know too much about identifying these in a picture per se, but you need to know the information about how many sigma and how many pi bonds there could be. So the only time you see pi bonds are when you have double or triple bonds, okay? By default, every bond has a sigma bond in it, okay? So if you have a double bond, there's going to be a sigma bond as one of the bonds. The other bond is going to be your pi bond. So a double bond has to have 2 bonds. It has to have one sigma, so then the other bond is a pi. A triple bond, okay, is going to have one sigma because every bond has a sigma bond, and then the other 2 bonds are going to be pi bonds, okay? So if you were doing this, all right, how could this be asked? All right, they could give you a particular structure and just ask how many sigma, how many pi bonds are in it. So for example, if you were given, okay, CH4 here, okay, I could ask how many sigma bonds, how many pi bonds are in this, all right? Well, anytime you have a single bond, all right, each of these bonds here are a single covalent bond. That's why they're just showing as a single line, all right? Those would all be sigma bonds, all right? So in this particular picture here, this would have 4 sigma bonds. Well, how many pi bonds are there? Well, none. You would not see pi bonds until you get to double or triple bonds, okay? So if I did another example here, if I did say this, and I said how many sigma, how many pi bonds here, all right? So I know that every single bond is a sigma bond, so there would be 1 sigma, 2 sigma, but then in this triple bond, there's also 1 sigma as well. So this would have 3 sigma bonds, but then 2 pi bonds, okay, from the triple bond. All right, so that's what you would have to be able to do here with sigma and pi bonds. You have to be able to say how many there would be by looking at a dot structure or a structural formula.